Now we're doing MHD waves. So we did sound waves. Sound waves are nice. Sorry, I'm trying to decide if I'm going to do it without looking at my notes. I'm going to try to do it. So, okay, sound waves, we had d by dt of rho plus div rho v, and we have, sorry, I'm going to spend a second on my board management real fast. Oh, that which was written there was really useful. If you saw it. Okay, so d rho dt plus div rho v is 0. dv dt plus v dot grad v equals minus 1 over rho grad p. But now we have plus 1 over 4 pi rho del cross b cross b. This is now the Lorentz force. So this is the v cross b Lorentz force term. So this is a particle, sees a magnetic field, and it goes to the left. So what we did with sound waves, let's see, we are incompressible, so I'm not going to perturb the density, but I will perturb velocity. Velocity is going to be v naught plus v1, and the magnetic field is going to be b naught plus b1. Now these are all vectors. I'm going to say that b naught is in one direction. See, b naught as a vector is b naught, let's call it x hat. I reserve the right to randomly change that. So without loss of generality, I can say that my mean magnetic field is along x, just by rotating the coordinates. So if I have some system, say the sun or whatever, I'm going to look at a little patch of the sun, average the magnetic field, rotate my coordinate system, then I'm right. Yeah?
Is the perturbation also in x hat?
The perturbation is not. The perturbation is in all of them. So that one I can't generalize. So the mean field I can generalize just by turning my head, but then the perturbations go anywhere. This is a very good question. And actually the details of these perturbations are gonna be kind of hairy. So I'm gonna go through all of this, and we've done this a bunch of times already. So we're gonna linearize it, then we're gonna drop it into Fourier space, and I'm gonna have some wave number, I'm gonna have some frequency omega, and some wave number k. And the wave number k, what does this mean? Now it's a vector. It was always a vector, but we kind of ignored it before. I mean, it was just, we got an expression that said something like omega squared equals c squared k squared, and k was just a number that we had. That was just the size of my wavelength. Now it's a vector, and it's the size of the perturbation as well as the direction. So if I have a k going in this direction, it has some magnitude k. That's the size of the perturbation. And again, it's k, so big numbers are small, small numbers are big. But that's okay. So it just gives you the size of the perturbation and the direction of the perturbation. So this is like, oh, I forgot to bring the giant spring. I have this giant spring. Did I tell you guys about my giant spring? I have this giant spring that's really good for this, and it stretches clear across the room. But it's, I'll bring it in on Tuesday. And if you see me on Tuesday, be like, did you bring the giant spring? And I'll be like, no, I forgot, because I was talking when I remembered. But I'm going to try to remember bringing it. So the wave vector is the direction that the perturbation is going. So like when I'm talking at the wall, the wave vector of my perturbation is that direction, and it has a size that is the size of whatever tone I'm making. So if I just sang a D, then it would have a wavelength of, 4 meters, and it'd have a direction of that. Now, I'm not making plane waves. I'm making spherical waves, so my wave vector is actually is positional dependent because my wave's going out in all directions. Let's pretend we just got one wave in one dimension. Everything's super boring and simple. Plane waves. So our wave is a plane. So when I draw a wave vector pointing like this is a wave that goes like this. So it's like, and it extends in all directions in that way, and it has a wave fluctuatingness along it. Does that make sense? It will make less sense in a minute. If it feels like it makes sense now, I'm going to make it very confusing in a second. So the wave vector and the magnetic field direction and the velocity direction are all interrelated. So, okay, doing sound waves is straightforward and not super painful, especially now that we've done it a bunch of times. And this is basically the same thing, except this shit is a vector, and it makes everything three-dimensional all the way. It's just a three-dimensional problem. So we got to think about things three-dimensionally. So I'm going to draw a diagram that looks like this. And this is x, y, and z, my three-dimensional thing. Now, always make sure that your coordinate systems are right-handed. So x, y, z, x, y, z. Otherwise, things don't work. If you draw x and y and then z coming out at you, then that's a right-handed coordinate system. It causes weird problems if I call this z and this y because the curls don't make sense. But for this cartoon, it doesn't matter. So my magnetic field, there's this little bit of blue that's crushed on the floor. And I've mentioned before, magnetic fields are blue. There's only this little bit of magnetic field here, so I'm just going to do it just for this very most important derivation. But I feel so sad. It's the only blue chalk in the room. It's crushed on the floor. So okay, magnetic field is in this direction, and I can pick which direction that one's going in. I can pick one of them. I could pick K to be along one axis too, and some books do that. Also fine. But the way this book does it, we pick B as along X. Now the K vector is going to be at some angle with respect to my magnetic field. Turns out I can pick that too. And I can pick that K lives in the XY plane. All I'm doing is picking a coordinate system here. I'm not actually assigning anything. So I've got some mean magnetic field. I flick it with my finger of God, with my infinite plane wave finger of God. And it launches a plane wave as some random direction. I can just orient my head so that the field is in this direction and the wave is in a plane. Now my velocity vector is going to have some non-zero projection in the plane. The velocity vector can be wherever. So the magnetic field I fix along X, the K vector is in this plane, and velocity is going to be whatever it comes out. Does that make sense? I haven't started doing any math yet. I'm just setting up the vectors. So we've got B. We've got K. And we've got V. Okay. The reason I did this is because I'm going to point at this vector at all these things a bunch later. Normally I hate that section of the board. So we need all those things. So what do we do first? We just take those two equations and we drop in our perturbations. And we're left with d by dt of rho plus div. And then we go through all that linearization part, and I'm going to skip that. Rho naught. Div, okay, what's here? Rho v is in the equation. I need some combination of rho naught, V naught. There's no rho 1, we don't have any perturbations there, so it's just the rho naught. So we have rho naught V1. V naught is 0. So this is the only thing that this term can be equal to 0. So now I've linearized it. And rho naught is my background quantity, and V1 is my fluctuating quantity. Sorry, anxiety got the better of me.
Giving into the book.
Is that?
Giving into the book.
Just to make sure I get started right. It has to be that. It's only one page, but I spent an entire day on it. Right, sorry. I knew I screwed something up. Because we do perturb density. But it goes away real fast. Anxiety was right this time. Sometimes you gotta listen to the little voice in your head, and sometimes you gotta not, and that's a hard thing about being a grown up. Okay, then the next one, dv1 dt, has to be v1 because that's the thing that I care about. Plus, okay, that term goes away, the v dot grad v term, we're gonna throw that out because it's second order. Words are hard. And then I've got this 1 over rho grad p. I'm going to do a bunch of things to that. The rho goes to a rho naught plus rho 1, and then we linearize that and we throw out the 1. So that's just 1 over rho naught. And then we're going to get rid of the p, and that's going to turn into a c squared grad rho 1. So I just wrote this down, but it's actually a pretty heavy combination of things. But we've done that already a couple of times. Plus 1 over 4 pi rho naught del cross okay. There can be only one answer here. I'm going to write down a b naught and a b1. Now you can go through and formally spill out b equals b naught plus b1 and think carefully about when every term goes away, but the only thing that can be there, grad b naught is 0, so there's no b naught in this term. So this one is b1. And here, I can't have a 1 because that's a second order term, so this is b naught. Now I have my linearized equations. Oh no, I don't have all of them. What am I missing? How many unknowns do I have? 1, 2, 3. What's my last equation? I have 2 equations. I need 3 equations if I have 3 unknowns, right? Otherwise, it's an undetermined system. What's the third equation? Somebody yell something. Where does B come from? The third equation is the induction equation, which I forgot to write down over here, which I'll do. d by dt of B equals del cross V cross B. This looks a lot like the vorticity equation because nature was kind and gave us this nice symmetry. Or it's a vector field and it has to do this. I'm not sure which. But it's this beautiful symmetry. So I linearize that. Okay, what goes here? I got a V naught, which is 0. I got a V1, which I know. I got a B naught, which I know, and I got a B1. And the combination of that with that is going to give me something that's second order. The only thing that goes here is V1 cross B naught. There's not a, there's nothing else that could be there. So what I'm doing is I'm taking that term and I'm plugging in V equals V naught plus B1 and B equals B naught plus B1. You just plug these into the induction equation and you're left with this. Everything else drops out. Do stop me if you feel, if I say something and lose you. This is too many equations. This is terrible. Okay, let's take the time derivative of this one. And then what's that do? I'm going to have a second derivative of time here. That's going to be part of my wave equation. This one is going to be a grad d rho dt, which we're just going to stick this in here. So I'm going to get a d rho dt. I'm going to stick it in there, which gives me this. So that's going to turn into a square. And I'm going to db dt. I'm going to stick it in here. And I'm going to have a really awful vector expression with a bunch of crosses in it. It's going to look like I'm sorry, I'm trying to make a joke that has a bunch of crosses in it that doesn't become offensive very quickly.
Sounds like you're at a crossroads.
Ah, there you go. So you can tell what a terrible Southerner I am. We drove past a church and my kid was like, "Why is there a big plus sign on the top of the building?" Probably going to hell for that. If there was such a place. So anyway, so I've got a bunch of cross products here that are all going into this equation here, right? So we've got all these cross products that we're going to have. Okay, so this goes in here, this goes in here, and we're left with, and this is really why I got the book, because I'm going to screw this up. Let's see if I can one-shot it. d squared by dt of v1 equals, let's write this, actually, so the book pulls a stunt that is a really good stunt to do, but also kind of does a lot of the same time, a lot of things at the same time. I'm going to leave the rho naught on top. So c squared over, oh no, that rho naught goes away. This rho naught cancels this rho naught. And I'm just left with c squared div v1. You can everybody follow that? That's div squared v1. Why is it div squared v1? So I take the time derivative of the Navier-Stokes equation. This becomes grad of d rho dt. I just stick in div rho, so that becomes div of div rho v. The rho naught cancels, and I'm left with grad squared of v1. Everybody good with this term? Now this business, does he do anything else? No. I got my 1 over 4 pi rho naught. Okay, we're going to kill this rho naught in a second because it's kind of boring here. We're going to kill the 4 pi too because they're boring. And we can learn something really interesting. But let's just write down what this whole thing is. This is del cross, okay, I got del cross stuff on the inside. Del cross v1 cross v naught cross v naught. Okay, so this is the curl of the cross product cross with v naught. This is an awful term. So we'll use a vector identity and blow it up. But we'll do that in a second. I'm going to first get rid of this business here. And also anticipate the result. So there's this beautiful result. Hans Alfvén is one of my favorite physicists. His name is all over MHD because he did it all first. So the Alfvén speed is, so I got 2 copies of B. I got a B naught and a B naught. And 1 copy of rho naught and 1 copy of 4 pi. So I'm going to define the Alfvén speed VA as B naught over the square root of 4 pi rho. This is important. Now, I haven't shown you yet, but this is the speed that waves travel up the magnetic field with. So I'll show you this in a second. So if I do this, then this equation becomes more simple. It becomes d squared by dt of v1 equals minus c squared del squared v1 plus, not a lot simpler, del cross v1 cross va cross va. And the parentheses are here, and those are very important to be in the right spot. So this cool thing is that dimensionally, b naught over square root of 4 pi rho is a velocity. Why is a Gauss over the square root of a density equal to a velocity? My brain doesn't really care for that, but that's what it is. So we have this vector identity equation that we're going to park over on this over here. We're going to come back to that in a second. Or we're going to leave that there and talk about it. Oh man. One of these days I'm going to gish my fingers in between these boards and it's going to suck. I'm going to have to teach a whole class with a bloody finger. Okay, so what do we do with this equation? I'm going to write this equation again neatly. d by dt squared of v1 equals minus c squared del squared of v1 plus del cross v1 cross va, all that business cross va. And then I'm going to expand this out with a vector identity. I think we got to use two vector identities, but it's not really painful. They're the identities that are in the back of the book. And we're going to say d by dt becomes minus omega squared, and d by dx is minus k squared. Same Fourier analysis that we did before. So what are the free parameters here? The only free parameters are v1. I've got 3 v1s and 2 vas, but there are no other fluctuating fields. We got rid of those by plugging this guy in, these guys into here, right? Which is the same thing we did for sound waves. Except we did it for density instead of velocity, but whatever. So this horrible triple product, we expand this out, so we do these two things, and two, we throw in a vector identity. Now I'm going to erase both of these things for board real estate. You don't have to. So then this becomes, nope, the d by dt becomes a minus omega squared. Let's leave the v1 there for a second because we need it. Let's see. Yeah, okay. There's a little bit of algebra in here that I'm skipping. So you can't quite see how these things are connected. C sound squared plus VA squared times div, no, there are no divs anymore, only Ks, times K1 dot VA times K plus VA dot K plus VA dot K times VA dot K times V1 minus VA dot V1 times K k dot v1 times va. Okay, so this term goes like a div v, k1 times, so no, that's v1. This should be a 1, not an a. Do it like it's in the book. K dot v1, that's just div v, right? Div v becomes k1, k dot v1. Is there anything else in here that I need to talk about? And then in the second term, we have a v1, this is a vector. We have a k, that's a vector. We have a va, also a vector. And v1 gets a va dot k, k gets a va dot v1, and va gets a k dot v1. So there's this nice symmetry to this where you've got all three vectors that we care about kind of having a party together. So what's the easiest thing we can do? The easiest thing we can do is throw a bunch of stuff out and yeah, is there anything else I need to say about this equation here? This is one of those equations that I've spent a whole bunch of time taking apart, and I know that there's things that I want to say right here, but I didn't write them down. So let us assume initially that K and V1 are perpendicular. And what does that mean? That means that I've got a magnetic field, which again ought to be blue, and I've got my wave vector. My wave vector is somewhere in this plane, and my velocity vector, so this is B, this is K, and this is V1. So if we assume that K dot V1 is 0, then this term goes away, and this term goes away. And we're just left with minus omega squared V1 equals VA dot K, right? Yeah. Is VA dot K squared. The V1 goes away. Oh, not a minus sign. Sorry, not a minus sign. So you assume that the wave vector and the velocity and the magnetic field are all perpendicular for a second. This is one solution. Now, this wave equation actually supports many waves. This supports 3 waves, whereas the wave equation that we got for sound waves only supports 1. But from all of these vector nonsense over here, we have more waves that we can support. So let's talk about the first one, and then I'll talk about the second and third ones. So this, if we make this assumption, this is called an Alfvén wave. And you can see from this, omega over k is just VA. And remember what VA is. VA is B naught over 4 pi rho, square root of that. So the Alfvén velocity is just equal to the magnetic field strength, modulo the density. So the Alfvén wave travels, sorry. K is along B. For an Alfvén wave, I drew it wrong. K is along B, and V is perpendicular to B. So what does that mean? How many of you guys play guitar or some stringed instrument? Any of you? A couple of you, a little bit. So you know how when you play guitar, you got a guitar, it's anchored at the nut and the bridge. you perturb it perpendicular to the string, right? So I have a string. Let's pretend this is guitar string for a second. It's really a magnetic field, but it behaves the same. So if I flick this in this direction, that disturbance goes along the wave vector. K is that way, V is this way because it goes like this. So the string is going to oscillate back and forth. The velocity is perpendicular to the magnetic field or the guitar string. The physics is identical. It's kind of rad. Magnetic fields have all of these cool similarities. So the velocity is perpendicular to the magnetic field and it travels along the magnetic field. So that's an Alfvén wave, and it travels with a speed v Alfvén. Now this is the most important one of the waves. This is also the only one that doesn't have a sound wave stacked on top of it. So this is a purely magnetic disturbance. There's no sound speed here, just the Alfvén speed. Oh, I'm way over time. Like 4 whole minutes. Thanks for listening. This is the important one. I'll talk about fast and slow waves on Thursday. And I'll give you an opportunity to ask more questions about this. See you Thursday.